Hi guys, this is Mr. Mitchell. Today we're going to be talking about ions. So just really quickly, we want to review this idea of valence electrons. Remember that valence electrons are the ones that are in the outermost shell of an atom, and we can predict them using the periodic table. So I have a picture down here of lithium, right? Lithium is in the first column of the periodic table, and so we see on his outside shell, he's only got one electron out there. So, sodium, potassium, rubidium, hydrogen, they all have one electron in their outside shell because they're in the first column. This is really important because the valence electrons are going to be the kind of the root of how these ions form. So what is an ion itself? An ion is just an atom that has a net charge. So up until this point, we've talked about neutral atoms only. So we've talked about atoms that have the same number of protons and electrons. Protons are positive, electrons are negative, and since they have the same number, they just cancel each other out. Well, an ion is not the same anymore, right? He's got a net charge. It means it's no longer neutral, which means that the protons and the electrons are no longer canceling each other out. So something has had to have changed here. There needs to be a difference in either my number of protons or my number of electrons. So the reason that ions form is to become stable. So all atoms will undergo reactions. They'll react with one another to become stable. Once they reach that stable state, they tend to not really react with anything else because they're happy. They're good the way they are. So all atoms desire to be stable, and once they interact and reach that state, they won't react any further. Or they don't want to react any further. So in order for an atom to reach that stable state, he has to have 8 valence electrons, or 8 electrons in their outside shell. To achieve that state, right, they can transfer electrons either to other atoms or to pull in electrons to themselves to get to that magic number of 8 on the outside. So fluorine, for example, fluorine would be in the 7th column on the periodic table, and so he has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Well, he wants to get to 8, and so in order to become stable, what he'll do is he'll pull in an extra electron and it'll just sit right there. And now he's got 8 in his outside shell and he's happy. But you see how that creates the imbalance with the protons and the electrons, because we started with 9 protons that are positive, and we started with 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, but we just pulled an extra one in, so now he actually has 10 negative electrons. That's a problem, right? That means that the atom's going to have a charge on it. I have more negatives than positives, and so I end up with a 1 negative charge. And that is what an ion is. Something that has a charge because he's changed his number of electrons. So we can predict, like we said, the valence electrons using the columns on the periodic table, and that's what eventually we'll use to figure out what the ion charge is going to be for every single element. So in order to become stable, we said that atoms want to get to 8 valence electrons. Well, if you remember, right, that the column tells us the valence electrons and we kind of skip this middle section, then 1, 2, 3, 4, 5, 6, 7, 8, they're all trying to get to this noble gas column. That's where they want to go. So they could go forward to get there, or they could kind of jump backwards to the line previous and then get there that way. So what they'll do is actually the least amount of work that's necessary to get to that noble gas column. As far as the charge of the atom, I follow this very simple rule, just a mnemonic device, LEPGen. It doesn't really mean anything other than it stands for lose electrons positive and gain electrons negative. So LEP stands for lose electrons positive, like I said, lose electrons positive, LEP. And what this means is that certain atoms will give electrons away to get that 8 on their outside shell. So sodium, for example, has 1 valence electron because he's in the first column. We just said that he can either, to get to the noble gas column, he can pick up 7 more extra electrons and bring them all into here, or he can just take that 1 and say, see you later, give it away, and then what's left? 1, 2, 3, 4, 5, 6, 7, 8. So he'd be happy if he just gave the 1 away. What's easier for him to do? Pick up 7 extras or just give 1 away? Giving 1 away is a whole lot easier, so that's what he'll do. So he started with 11 protons. And he started with 11 electrons, but we just took this one and said, see you later. So now he's down to 10 electrons. What happens to his charge here? 11 positives and 10 negatives. I have a 1 positive charge left over. So if I lose electrons, I end up with a positive overall charge. Now, chlorine's kind of on the other side of the spectrum. I gain electrons, I get a negative charge. So chlorine has 7 electrons on his outside shell. 1, 2, 3, 4, 5, 6, 7. So he can either, to get to 8, pick one extra one up, or he can give those 7 away. What's easier for him to do? Pick up 1 or give away 7? It's easier to pick 1 extra up. So what he'll do is pick up that extra electron. It'll sit right here. And so he started with 17 protons. And he started with 17 electrons, but we just got an extra. So now he has 18 electrons. So what's his charge going to be? Well, I have 17 positives and 18 negatives. That's an extra negative. Now I have a 1 negative charge. So if I gain electrons, I get a negative charge on my ion. So there's special names for these two types of ions. I have a cation, which just means that it's positive, and an anion, which just means that it's negative. So it's just a quick way for people to speak about ions and reference exactly what their charge is without having to say, oh, well, I have sodium with a positive charge. I have sodium with a positive 1 charge. It's easier to just say a sodium cation. And now we know, okay, the charge is going to be +1. I know that he's got a positive charge. One real, silly way to remember cation versus anion. Somebody showed me this in college. I can draw, just a positive plus sign in the middle there, and I draw a little cat out of it. And I know that he's got that plus sign in the middle for his nose, and that's a cation. It's something silly, but maybe that's something that'll stick in your mind and help you to remember that a cation is a positive ion. So as far as ion notation goes, it's just like isotopes. When we're talking about elements, nobody knows if we're talking about an isotope or an ion unless we tell them about it. So when we reference ions, we have a special way to write them so everyone knows that we're dealing with an atom that has a charge and not a neutral one. So the symbol is actually really easy. It's something so simple. We're going to use the same letters, all right? So sodium is Na. But instead of just leaving it like that, we're going to use a superscript to show what the charge of that ion is going to be. So sodium, remember, he has 1 on his outside shell, so he'll give the 1 away. When he gives 1 electron away, gain or lose electrons positive, so he's going to have a +1 charge. All right. So in order to designate that, I would say sodium +1. He's got a +1 charge. Or I could write sodium 1+. It doesn't really matter what you do because you're showing me the same thing here. It has a +1 charge. In fact, when there's only 1 there, you could just write it without the 1 at all. Just like in algebra, you don't have to write 1x, you can just write x. We can just do Na+. So any of these is acceptable for one that has just a charge of 1, but when we start getting other charges, you have to include the number in there. So ion notation is just the symbol, and then we put the charge up in the corner like that to designate that we're dealing with that charged ion. Just going to practice real quick with a couple of these just to make sure we're on track with it. So we want to know what ion will an atom of sulfur most likely form. So first we find sulfur on the periodic table because we need to know how many valence electrons he has. Sulfur is right here. It's in the 6th column. Okay, so he can either gain 1, 2 to get to that noble gas column, or he can go back 1, 2, 3, 4, 5, 6. Well, is he going to gain 2 or lose 6? It's probably easier for him to gain 2 than to lose 6, and so we'll expect that he's going to do that. Now remember that sulfur's atomic number is 16, so he started with 16 protons, and we said now he's going to gain an extra 2 electrons, so instead of 16 electrons, he's actually going to have 18 electrons, and so what's his charge going to be? 16 positives, 18 negatives, he's going to have a 2- charge. All right. So if I were to draw this out, sulfur's symbol is S, and I know that he's going to have a -2 charge, so I'd write 2 negative up here, and that is my ion notation. Let's do one more. What ion will an atom of calcium most likely form? So now we find calcium on the periodic table. Okay, we see he's here. He's in the second column, which means he has 2 valence electrons. All right, so he can either gain 1, 2, 3, 4, 5, 6, or he can just give away 1, 2. Easier to gain 6 or lose 2. He's probably going to lose 2. So just looking at what his atomic number is, he's got 20. So we started with 20 protons. And he just gave 2 of his electrons away. So he's down to 18 electrons. So what's his total charge going to be? 20 positives, 18 negatives. He's going to have 2 extra positives. And so we just take his symbol and we'll write Ca, and the charge is 2+, so we'll make that a superscript up here, and that is my ion notation for calcium. So at this point we've practiced, we've defined what an ion is, we know how to find it using the periodic table and the columns to determine valence electrons. We know that in order to become stable and form an ion, we're trying to get over to the noble gas column, so we can either move forward or back, and we'll do whatever is the least amount of work. And once we've done that, we can predict the charge on the ion and write it out in this notation. So hopefully this is helpful, and that's all we're going to talk about today.